to go. Okay, we are set. Folks, welcome everybody to the Profiles in Technology MudMotor Forum. I'm Jim Overkirker, I'm Executive Director for IDD. We've got a very esteemed panel here today. And okay, we are set. Okay, hold on a second. Folks, welcome. Need to mute that. YouTube shows, it listens up in the background, so I get the feedback. So I got to mute that.
Yep.
Let me go over, I'll hit our schedule real quick. Okay, so you see we have a quick introduction here this morning. Session 1 is on lower ends with Bill Murray. We have this 2 10-minute presentations, and then we'll have a Q&A session. So if you didn't hear us talking a little bit earlier, you can put your questions in either the Q&A or in the chat. If you have a longer question and you would actually like to speak, just raise your hand. You'll see a control at the bottom of the screen that says raise your hand. If you do that, then I'll give you the opportunity to speak, or you can send me a question in the chat as well, and I'll do that. Then session 2, led by Farhad Hamadov, is power sections. And again, 2 10-minute presentations followed by a 10-minute Q&A. And then we have a unique motor design sessions led by Scott Dixon, and again, a Q&A session after that. So without further ado, I will turn it over to Bill Murray.
Good morning, fellas. The first session we're going to go through is going to cover the lower end of the motor, and we have 2 speakers today. The first one was Imuche from NOV. He's going to cover NOV's new Series 50 lower end. So Imuche, you want to take it away and explain to us the new lower end?
Hey, good morning, guys. Thanks for having me. Let me see if I can go ahead and share my screen, and you just confirm to me when you can see my presentation.
I'm seeing a lake with, yep, it's showing up.
Okay, that's sorted out. So again, good morning, guys. My name is Gazier Imuche. I am the engineering director for downhole for the drilling motors product line, or the drilling tools product line here in the Houston area. So this morning, I wanted to talk to you a little bit about some of our lower end technology, primarily our Series 50, drilling motor. So when it comes to lower ends, NOV specializes in both mud lubricated drilling motors as well as sealed bearing drilling motors. And today we're going to be talking about our latest and greatest sealed bearing motor, which is our Series 50 platform. So our Vector Series 50 motor is our strongest and newest, most reliable drilling motor that was designed primarily to maximize performance and reliability while still giving you the steerability for motors technology. It's designed with a short bit to bend to not only get you the curvatures you need to get, but to ease rotation in lateral sections. And so by reducing our bit to bend or designing a short bit to bend motor, you can still get the curvature you need without having to dial up the adjustable bend setting to a high degree. And that allows you to rotate in the lateral without putting so much cyclic loading or forces on your motor. It allows you to drill a tighter curve, and for different applications like in the backend, we're able to do single runs, curve to laterals, because of the unique bend setting and ability to rotate in the lateral. So we've designed this motor to be able to take the highest torque power sections. As you guys know, there have been constant improvements in power section technology, coming out with higher torque, higher flow, higher speed power sections. And so when you're designing lower ends, you have to constantly keep up with the power section technology so that you can run any kind of even wall, hard rubber, constant wall power sections that we have now in the industry. And so if you compare our Series 50 design to our Series 36, which is our previous technology, for example, on the 5 1/8 tool, we have been able to increase our torque capacity by about 68%. And on our 7 1/8 motor, we've been able to increase our torque capacity by about 35% when you compare it to our 6 3/4 Series 60, Series 36 drilling motor. We've also not compromised anything in this technology. We have not compromised any of the all life. We have better capabilities for on and off bottom capacity. And we've been able to do this by having a unique parallel stack design that allows us to include all the benefits that you are accustomed to in our Series 36 and improve upon them without sacrificing anything on the mechanical side of the tool. If we take just a quick look at some of the features compared to our Series 36 bearing assembly, if we compare a 5 1/4 Series 50, for example, we know bit to bend is a measurement everybody's familiar with and likes to know. If you look at our Series 36 bearing pack, we used to have a bit to bend of 61 inches with the adjustable assembly and 53 with a fixed bend. But with the Series 50, we've been able to come down to 50 inches with an adjustable assembly and 46 inches with a fixed bend assembly. And similarly, if you look at a 7 1/8 Series 50 and you compare that to our legacy 6 3/4 Series 36, on the Series 36 with an adjustable assembly, we had a bit to bend of about 76 inches. And when you use a fixed bend assembly, it comes down to 64. But if you look at the Series 50, we've got a bit to bend of 60 inches with an adjustable assembly, and then 52 with the fixed bend assembly. And so we've tried as much as possible to give you better beat to bend features to improve the curvature you get without compromising anything on the assembly. And so with any new technology, we're continuing to see adoption in different basins, primarily in West Texas and in the back. And as we continue to move from our legacy Series 36 assembly to the Series 50, we continue to accumulate the amount of runs we're seeing. Right now, we're primarily participating in the North American market. And for our 5 1/8/5 1/4 tools, we have about 380 runs to date. That continuing as customers continue to shift from our Series 36 to our Series 50. And for the 7 1/8 tool, we've got about 1,100 runs to date. And this is up to February of this year. And so we continue to see customer adoption with our Series 50 because of the advantages it gives our customers. And our goal is to continue to grow that until this becomes our primary sealed bearing technology. So some of the features or design concepts that went into our Series 50 is we used our bearing mandrel, or some people call that the main drive shaft, and we integrated the lower end of the universal joint. And what that allows you to do is to eliminate the threaded connection you have there. And that gives you more material to increase your torque capacity of the overall assembly. In the past, we had seen occasions where we had pin fractures in that particular section of the tool when we've run older bearing assemblies. And in order to eliminate that completely, we have completely removed that connection. And so we've got beefier, high alloy steel material that allows us to increase the torque capacity and eliminate one additional connection within the motor. We've also improved on and off bottom capacity, primarily the on bottom, which you're drilling with, by about 28% compared to our 6 3/4 Series 36. And like I said before, we have a lower, shorter bit to bend, robust pack. As you know, with NOV, we have a history of sealed bearing technology. So we've taken all the lessons learned from the 15 and 20 years that you've seen our Series 36 bearing assembly. We've taken all the good things from that, incorporated some new designs to make this Series 50 more reliable and a better performing motor, and put that into a short, robust bearing pack with proven field technology. We also redesigned our drive shaft assembly for the Series 50 technology. Some of the legacy drive shaft assemblies use a ball and pocket type U-joint. And what that does is when you're transferring torque, it gives you a line of contact across, which can produce high stress in the pockets. And so what we've done is that we have redesigned the drive shaft completely to give you flat, torque carrying surfaces. And we also increased the shaft diameter by about 25%, which is directly proportional to your torque capacity. And what we've done is we've given you a smoother transfer of torque from the power section, and that reduces the chatter you see in the bearing assembly, especially when you run rotary steerable applications and you experience any kind of stick slip. You'll notice that when you tear down the motor, you can see signs of chatter. But by having, a flat torque carrying surfaces, removing any lines of force contact, we've been able to give you a smoother torque transfer while still maintaining the articulation you need for giving you different bend settings. And so you still have your, 0 to 3 degree adjustable to give you varying bend settings and dog legs, but we've improved the technology of the drive shaft itself to make that more reliable. We also improved the technology of the seal caps and our seal boots by working with our local elastomer team by developing different polymers to make seal boot materials. We also redesigned the locking feature of the seal cap, which makes sure the seal boot stays in place. And we actually have a mechanical lock now that is not exposed to any kind of rubbing, and that will make sure the seal cap stays in place and cannot break free due to any vibration that the motor sees. Moving outside to the external of the motor on the adjustable section, we do understand that there are occasions where the motor has to be adjusted, on the rig side, and we've tried to make that a simpler and more reliable process. And so in the service shop, before we send the tools out, we now incorporate a lock-in pin to prevent the mandrel or the spline mandrel or the inner housing from moving when you're trying to adjust the motor on the rig. And so it locks everything in place. And so the motor doesn't rotate relative to your bend setting. So that gives you an easier way to adjust it on the rig floor. And we also have obviously visible markings on the adjustable that line up directly with the short side, so that you know what bend setting you are and you know precisely what angle you're adjusting the motor to. And so just going through the lower end, the bearing assembly itself, the drive shaft assembly, and the adjustable for our Series 50, we've taken the time to make improvements to every aspect of the technology to make sure we can deliver a reliable product, a product that will meet our customers' expectations, and a product that will give you, a lower cost of ownership over time. And like I said, as we continue to see adoption with this technology, we continue to get performance summaries or positive results from our customers. This particular one was using a Series 50 motor to drill, back-to-back record runs in Reagan County, which is in West Texas. And we reached, TD, saving the customer a trip with an average ROP that was, 58% higher than offset, or 32% increase in ROP over the top 5, performers. We also have other performance summaries where we have the Series 50, working with our agitator system, which is our friction reduction tool, to give the customer a record run with improved ROP. And so when it comes to compatibility, our Series 50 is compatible with any friction reduction type systems. It is compatible with any, RSS system. We have maximized the radial support at the lower end of the tool so that when you have an RSS below the motor can still handle any kind of bending loads that it sees. As with a sealed bearing assembly, you've got 100% flow to the bit, so you don't have that pressure loss, between the motor and the RSS system. And so we hope to continue to see, these kind of feedbacks from our customers as they continue to use the Series 50 technology. Just one more to show you guys. This is a performance summary for another Series 50 using a 7858 ERT, which is an even wall power section in the Permian. And so the Series 50 has been designed to work with even wall power sections and any power section that is in the market right now. And we know that power section technology continues to improve. Elastomer technology continues to improve. And so we don't only design the Series 50 for what's in the market today, we design it for what's in the market to come. And so we're pretty confident that with the introduction of new power sections, our Series 50 technology will be able to be run with any new power sections that are coming out. And lastly, we've got, tech sheets available for anyone that wants, more information about the Series 50 technology. We've got our downhole website that anybody can go to. You can send an email to downhole@nov.com, or you can go to nov.com/downhole for more information about our technology. And so I just wanted to spend a few minutes with you guys and give you a top level highlight of our Series 50 technology. And if you have any more questions, please go to the website, shoot us an email, and somebody from NOV will reach out to you and be willing to answer your questions.
Well, thank you very much. That was a very informative presentation. It's a pretty impressive looking motor. And now we'll go over to Emmanuel, who's going to talk about BICO's fit for purpose, bearing assembly to go with the even wall power sections. Emmanuel.
All right, thank you, Bill. I'm just going to start the presentation. Just share my screen.
Okay.
Emmanuel, quickly, we actually didn't talk about this, but you had the two sections, so obviously talk.
Yes. I'm going to transition. Okay. See if you guys can see my screen here. Can you guys see my screen?
Yes.
Okay, good. Slideshow. All right, good morning, everyone. My name is Emmanuel Omojua. I am the Director of Engineering here at BICO Drilling Tools. Just looking over the R&D and sustaining of downhole drilling products, mud motors, jazz, shocks, vibration tools, circulation tools. Today, I'm going to be talking about the integrating even wall power sections with a fit for purpose lower ends to improve reliability. And as Bill introduced me, BICO is known for premium, models, especially with the even wall power section we provide that generates that high performance in terms of horsepower and you can run that with just any lower end in transmission or in bearing assembly. So this is something BICO, wants to be differentiated for, that we can put an even-walled power section on fit for purpose, lower end that is designed to take that high horsepower. So before I dive into lower ends, I'll talk a little bit about the current state of MudMotor operations, then talk about the transmission, what we're doing on the transmission and the fit for purpose bearing assembly we have, and transition back to the even-walled power section on the next section of the meeting. Where we currently are in terms of MudMotor operations, and this is coming from operation requirements, what customers want to achieve, higher rate of penetration. We want to do fast break records, higher flow rates, and BICO, we respond quickly to that in terms of power section development. And once we develop a new power section, we also have to make sure the lower end is reliable to be able to transfer that load from the power section to the bit or any tool below the model. High torque is always a requirement. A high load transfer in terms of that thrust which the power section is delivering. Also weight on bit on the bearing assembly. We're able to plan a design around those operational requirements. We'll continue to see a lot of dysfunctions, downhole stalling, stick slip, the high frequency torsional oscillation. How we responding to that, and it's all putting back those field observation back into the design process, closing the loop real quick, decreasing overall length of the tool, and providing that short bit to bend is always a requirement. And BICO has some of the shortest bit to bend, in the market. Currently, we're able to go to high dogleg severity, which we plan for in terms of fatiguing on the housings and connections. We design around that, use appropriate materials on our tools and all the mandrels. Increase down temperature. We want to be able to offer power sections that will be able to, for the elastomer to withstand those high temperature when they're exposed to as high as 400 degrees, downhole. We're seeing a lot of frictional wear from formation contact, and that comes back to some of our hard-facing applications and our kick pad or bearing housing. So this is currently what customers are throwing at us, and BICO is taking all of that back into the design process and also operational offerings. To dive into lower ends, we were just talking about transmission on the NOV model. BICO, like I said, BICO's set apart for this high horsepower power section. So once customers know you have that even-walled power section on your model, they want to push to the limit because they know you can deliver the torque. But the thing about it is, no matter how great your power section is, if your transmission is weak and your bearing assembly is unreliable, that's going to be a disaster waiting to happen. So from BICO engineering standpoint, we'll, as much as we develop new power sections, the engineering on the lower end is top notch in terms of how we incorporate that into our design, analysis, designing for the bending, moment coming from the power section, torsion from, that high torque you're putting out, flex shaft, CV and the hybrid CV transmission as some of the application-specific transmission we're able to provide to our customer based on their goals. We'll continue to develop research into new materials, tougher materials that can withstand and even go beyond what our power section can deliver. So we look into the future and see what the next generation in terms of horsepower requirement is, and we're preparing ourselves for investing in reliable materials that can provide they can transfer that horsepower to the bit downhole. FEA and CFD verification on all our designs, from the bit box up to the top sub. We verify, make sure we are theoretical, as close to our dyno operations, dyno testing. So this goes through those dyno testing, field validation. So on the transmission side, so we're able to match transmission now with the horsepower coming from the Even-Wall. On the bearing assembly, this is BICO's next gen bearing assembly. It used to be called a G2, but this is a B5. It's the fit for purpose bearing assembly for the Even-Wall power section. And one of the things that I'm going to show is kind of a must in the design and sizes as we size up or size down, just to match what the power section is. We make sure all our drive shafts are made out of forgings, high strength, fatigue resistant forged drive shaft. We ensure, we've transitioned to double shoulder connections, just so we can be able to transfer, more torque and have that improved torsional capacity on connections, and also increase the fatigue resistance. We've seen increase by over 40% in amount of torque we can deliver, coming from going into this new generation bearing assembly. Toughness on the upper mill bearing is also something we've improved on, and a lot of optimization, design calculation has gone into positioning your radial supports on your connections. In previously, we were breaking those connections. They were straight connections, and the bearing, upper mill bearing were not really optimized in terms of positioning, and we've been able to make sure we support our connections from radial loads and avoiding that failure downhole. Radial bearings, we're able to maintain a low bypass as high as 1700 PSI differential, even when we go pin down on rotary stereo tools. We maintain our fits, downhole, and this is also coming from planning. We have a model that we just recently developed that we provide to customer on our app, and I'm going to talk about that later on for them to plan for the bypass, downhole, and be able to also go back to after tearing down the model just to assess in terms of change, and we will see that we were able to hold this fit pretty constant throughout the run, and we're engaging our vendors on developing new hard-facing, new bearing materials, just so we're able to deliver that fit optimization even as we go downhole. On the truss bearings, one thing we've done is on the high load, because like I said, our customers push, once you have that Even-Wall power section, it's just a license to push on the model, and we're really fine with that. And all it does to BICO is make our models better, at competition. So we have customers that will exceed, weight on beat, and truss bearings will tear up, and we go back. So what we've done recently was just to optimize the geometry on the truss bearing bases and ball contacts, just so we can provide higher truss capacity on and off bottom. On the drive catch system, drive retention system, we have a metal-to-metal system that will really activate, once we have, in the case we have a failure downhole, we try not to leave anything, slipping out of the model downhole. Our DRS system is really good and effective in doing that. Metal-to-metal sealing on the drive shaft and the lower mill bearings. Previous design had hole rings, threads on threading the lower mill bearing to drive shaft, something we we've moved away from. We're going with the metal-to-metal sealing system, and that prevents washing or slippage of the lower mill bearing, and just we can improve reliability on this bearing assembly. On the bearing fluid bypass, we recently developed a CFD model, and we're currently testing, testing this in the lab, going just so we can, go back and match the data. So we're able to predict, the bearing fits as we go downhole based on your fit, bearing fits, flow inlet, and also we would like to know what the PSI differential will be below the tool. And we're just going back to look at the velocity profiles through the bearings, the pressure losses across the radial bearings, and this is offered on our on BICO app. If you go on the Apple, Apple Store, or also on Google Play Store, you can get that bearing bypass calculator. It's part of our on our product app. All right, I think that's all I got on the lower ends. Just that if there's any question or transition. Thank you.
Well, thank you very much, Emmanuel. That was quite informative. It's nice to see, all the motor companies upgrading the lower ends to handle the new power sections coming out and to deal with that. I mean, both you and NOV are covering that, and I guess in the second session you'll talk about some of the high torque power sections.
Yes, exactly. Right.
For it. Jim, how do we see the questions, or can you see the questions?
There should be, you see in the lower part of your screen, Bill, there's a tab that says Q&A. It's got a red 1 on it.
Yep.
Actually, Gozi answered the question, but we can.
Okay.
What are the flow rates for the S50 lower ends? And Gozi, I saw that you had replied, had a typed an answer. Do you want to go ahead and elaborate on that? You're going to have to unmute and turn your video back on, though.
Yep, I was talking to myself, but that's okay. Yeah.
Reverb.
Yeah. So just to answer Scott's question, on the 5 1/4 tool, we've consistently run 400 GPM. The tool is rated to 450. So we try to make sure that we keep up with the power sections. I know most of the 5 1/8, 5-inch, 5 1/4 power sections are anywhere from 350 to 400 GPM. So we're confident in 400 to 450. On the 7 1/8 tool, we've got power sections that run as high as 800 GPM. And so we hope to push that. Although in operations, most of the power sections out there run anywhere from 600 to about 725, 750.
I guess, Gozi, you're pretty much seeing that when you move the bar from a capability standpoint, that the operators and folks in the fields are pretty much pushing things to the limit. Is that right?
Yeah, that's correct. And what we want to do is make sure we have, the lowest cost of ownership for the tool. So we know that we have recommendations that we give to operators, but certain conditions, certain situations in your well may require you to flow at a higher flow rate, or to pull at a higher pull load, put more weight on beat on the motor. And so we want to make sure that we're always a step ahead. As Emmanuel said, there's a constant race in power section technology. And so if you're designing for what's in the market today, you'll be too late already. And so whenever we come up with a design, we're trying to make sure that we're at least, a step ahead of the power section technology. And with the, drill bit technology constantly improving too, I mean, you have to make sure that your lower end can take whatever torque, whatever flow, whatever weight on bit that the application determines. And so especially from a flow rate perspective, when you're dealing with your well cleaning, your AVs, we want to make sure that even though the customer doesn't need that much flow rate, if something happens, they don't have to worry about our motor when they do that.
Right.
And we know some customers may use a power section from a different manufacturer, and so we want to make sure that we can always be one step ahead of the game.
I think I have a note to myself to put together a session on mud motors versus bits. Who's stronger? And you know, that could be interesting. Of course, the idea is to collaborate, not to compete.
Of course.
But there does seem to be a competition as who can build the strongest component. And then of course, as soon as something gets stronger, then then people start pushing it to the limit. And I think we're seeing that with the performances in the wells that we're having.
Yeah, and the challenge is that you have some companies that specialize in manufacturing, designing, producing power sections, but they don't design bearing assemblies or drive shaft assemblies. And so obviously they're just trying to make the best product they have. And as a company that designs, bearing assemblies and drive shafts, you have to be cognizant to always keep up with those companies, because they're not necessarily thinking about you when they do their products.
Right.
Yeah.
You and Emmanuel had both. I'm sorry, Bill.
I think the operators are always going to take advantage of any new technology or new capacity in the tool. When someone comes up with a newer power section, like Emmanuel was mentioning, they're going to use it to its limits. And that requires you to, design a new, stronger, lower end. And then when you get that handling, the power section or the bit guys come up with something that can use even more power and torque. And it's a constant game of leapfrogging. But, the operators are going to push everything to the limit.
Yes.
Yep.
And that's the idea, is to be able to, it's 110 to 115%, right, Bill?
Yep. I think the maximum limits the motor guys put in their spec sheets are, the operators are just, it's a suggestion. A very rough guideline.
No, they want to make sure that they use that entire 25% safety factor.
What that is.
There's a question here, Oscar Sanchez. It says, not a motor question. For those flow rates, what type of MWD pulsar restrictors are being used? He's curious about that. Do you guys have any visibility to that?
No, I'm not sure about the pop-up valve settings or what the restrictor plates are. Something I can definitely find out from our MWD team, but I don't have visibility on that right now.
There's kind of two sides to that question, because with some of the more powerful pulsars and so forth that are in there, that you're seeing the pulsing having an impact on the motor performance. Higher flow rates, higher pulses, you may see 125 to 150 psi fluctuation when the tool is pulsing, and then that has an impact on the motors. Can you guys comment on that a little bit?
Yeah, so from a performance standpoint, a delta in pressure does not significantly affect the motor. I know some people also think that if you're bypassing flow rate above, you can change the speed of the bit, instantaneously. But our motors are designed to take those changes in pressure. In a real drilling situation, you don't have actually constant pressure on the tool. I mean, you're constantly bypassing and changing your differential across the motor as you drill. And so the motor is robust. It doesn't affect it negatively.
Good.
Because in reality, your weight on bit changes, dynamically as you drill. So technically, you're varying the pressure inside the tool. Yes, we'd like to think that everything is smooth and constant, but that's not a reality.
Right. All right, Manuel, you had mentioned earlier some of the materials and so forth. I see we have Mitch Zagonski on with Altus, the king of titanium. what are some of the types of materials that you're looking at now?
If I tell you, I'm gonna have to I'm gonna have to kill you.
That's why I asked you about it.
I don't think I don't think I can give that information away. But
That's why I muted Farhad so that he couldn't have a heart attack on it.
yeah. But it's we're engaging vendors and with the R&D team we have here, just exploring and sharing specs. What we find with vendors and seeing how to source, because one, it's a thing to find a sophisticated material. It's also another thing to be able to find it on the market. But we have vendors that are really very collaborative. But yeah, that's about what I can say on the materials.
Well, Emmanuel, I'd heard a rumor that you were using unobtainium.
Someone
you can neither confirm or deny that, right?
Yeah, that was what happened to me last week. Someone was, I think it was just, but advenium or actinium. I can't remember what material he said, and I had to Google it. And guess who came up on Google was Wolverine that came up. I was like, okay, my bad. Yeah, I had to Google that material.
Yeah.
So yeah, but
and unobtainium from was it Planet Naboo with the big blue people?
That's right. Yeah. Now I forgot what the name of the movie is.
Yeah, I can't think of it either. Avatar.
Yeah, that's it. It was Avatar. That's correct. I'm glad you did it. I've been sitting here scratching my head for quite some time. Emmanuel, I had to put you on the spot because I saw Kosei.
Yeah. Oh, yeah. I saw Kosei. I was like, you're going to make me lose my job today.
Okay. Well, you passed the test, Emmanuel. You passed the test. We have ways of making you talk.
Yeah.
Yeah, Tim Tate came up with Avatar. He put that up there in the Q&A. So are there any other questions? Bill, do you have any other questions that you'd like?
No, I don't have any. I think both guys did a good job, and it's impressive seeing the new motor technology coming out here. Whereas an old motor hand many years ago, back in the 80s and 90s, things were quite a bit different. So it's
that was
impressive.
The last century, Bill.
Yep.
The reason I know that is I was there too. So that's the
exactly.
Yeah. It's why don't you comment on that for a minute, Bill? We have just a few minutes left. I'm not necessarily just trying to kill time, but I saw something came up about the early dyna drills. Actually, it was Rabello was teaching his MudMotor class yesterday, and he was going through the history, and I remember the D500.
Yep.
And then the D1000 came out, and everybody couldn't believe it, and how strong that was. And I think that was maybe 60, 70 horsepower.
Yep. Yeah, I mean, we're talking about, Imuche was talking about, short bit to bends. I mean, when I got started, they were putting bent subs above straight motors to kick off, so you didn't talk bit to bend in inches, you talked it in, feet, 30, 40, 50 feet back, you had a bend. And then, the very short bit to bend assemblies that are out there today, the high power sections, when I started, there was just single lobes, and they were just coming out with multi-lobes. It's changed quite a bit. It's a constant race to keep up with the new technology and the drilling. They drill so fast these days.
Yeah, of course you didn't rotate a bent housing.
Yeah.
At least you weren't supposed to. I do know if you.
Yeah, no one would openly admit to doing it, but they did it.
Well, but those were also the days, Bill, that you got run off if you built stronger than 3 degrees 100, right?
Yep.
So it's different. But I want to commend you guys. From us older hands, it's great to see you sharp young guys come along and the work that you're doing, and I think it's very good. So we appreciate you participating in this, and kudos to the work that you're doing as well.
Yep. Thank you very much, guys, for
Thank you.
sharing with us in the industry today.
Yeah.
That's how we're going to advance the industry, is, building off of each other with technology and ways of doing things, and, disseminating information. So the people using the tools are knowing what's out there.
Oh, you're welcome, man. And, we're just building off of you guys' shoulders. So, thank you for having us.
Thank you for taking the time to share with us.
Thank you, guys.
All right, so Farhad, we'll transition into power sections, and Emmanuel, I guess you can just stay on because you're gonna be the kickoff.
Okay.
So Farhad, you can turn your video on as well, unless Kosei is right over your shoulder watching you. That might be.
Okay, you need to admit me because it says you have to turn me on basically because you're moderating the screen.
Yeah, be careful how you ask that, Farhad.
Okay.
You should be it, huh?
Yeah.
There we go.
On. There you go. Well, good morning.
You've got the con.
Yeah, good morning, and whoever is on the eastern side, maybe good afternoon or good evening. I know we have a few people that joined in. Our next session is on the power sections, and we do have 3 speakers. Evidently, and clearly that, we have definitely made some strides in the technology, and I mean, power section is definitely one of them. So I have 3 presenters. Once again, Emmanuel will start off with integrating high power even wall power sections with triple S with fit for purpose bearing assembly. Well, basically triple S technology on the power sections. Then we'll go with Hank Walters from Full Metal Power, and Scott Dixon will be talking about, from NOV, will be talking about 78772 power section as well. And, lower end was very informative, and obviously we are looking forward to hear more about power section. So I'll turn it over to Emmanuel to start off with the even wall technology.
All right, thanks, Farhad. Let me go back to sharing my screen. Okay, bring it up here. All right, diving into power section. We're getting some feedback. All right. So starting off with why even wall power sections, and for just to get people up to speed, the difference between the conventional power section and the even walled or thin walled power section is just because of the amount of rubber you have in the conventional compared to what you have in the even walled. You have that thin cross section of rubber through that power section. And compared to competition, we have the triple S and the double S technology. Our triple S is the one that provides, higher horsepower, and the double S also is very reliable. In terms of length, for the same length of power section or motor assembly, we get more horsepower. The triple S, double S is able to deliver more horsepower per inch, and we keep the assembly, your motor assembly as short as possible, even for handling on location, and that comes in handy for the big models. The 9.5, you don't want to get your motor assembly too long, and we're not able to pick it up on location. If I'm going to show our spec sheet on the next slide. One thing we see on dyno test, even before and after jobs, is we were able to hold that RPM even as we load up on that model for that high load. We don't lose RPM that much. It's always a very low RPM loss that we see on test. Reduced hysteresis, and that's coming from the amount of rubber you have, and I'm going to talk about a study on the next slide, what we recently completed on just studying hysteresis on this different elastomers or different power sections. A superior performance, I talked about the need to be able to have your elastomer withstand temperatures as high as 400 degrees. Well, BICO has a lot of applications in the geothermal business, overseas, and we have reliable, reliable power section. We stay in hole without a rubber disintegrating due to high temperature. This is what the spec sheet looks like. I was talking about the, and this we offer power section too for sale. Even as we use them on our MudMotors, we also sell to customers. On the RPM loss, as I was describing, we were able to hold our RPM with very less RPM loss, even as we load up the motor on differential. A study we recently completed was just comparing the two power sections based on just an elastomer point of view. We applied the compression feed between the rotor and the stator, some frictional contact, introduced drilling fluid, at about circulating pressure of about 300, and try to see how much of temperature buildup we see in the elastomer. One thing that was prevalent and which we see from operation, in terms of feedback, is that high temperature buildup in the conventional elastomers, and that's mostly evident on the center of the lobes. And that's where your chunking, mostly starts to happen when you load up your power section. And we see that high temperature buildup from hysteresis and also from convection heat transfer due to the mod convection transferring some of the heat to the rubber too. Another thing we see on the Even-Wall is that uniform, heat distribution observed in the, I think this is in the way, let me get it out of the way. One thing we see on the Even-Wall is that uniform heat distribution within the elastomer. That is really evident because we have that quick dissipation, because we have that steel tube behind the elastomer, and that has taken away that heat quickly from the system. And then we were able to keep the rubber, in the hole at high temperature, high load, even at that high compression fit. I think that's all I got on power sections. Just questions, discussions on, some of the offerings we have. If anyone has any question. Fahad, hello.
Okay.
Any question?
There are no questions that have popped up.
Okay, on hand right now.
Catch, we have a Q&A session there too.
Alrighty, yeah. I'm still gonna hang around. Yeah.
All right. Can everybody hear me?
Yeah.
Okay.
Yes, I can hear you.
Well, yeah, thank you very much, Emmanuel, for talking about the Even-Wall power sections. We definitely have come far. So I'm going to turn over to Hans now, who's going to talk about full metal power. And be very interesting to hear as to see where metal to metal and where we, this is a very hot topic nowadays. So turn it over to Hans to see what he has in store for us.
Oh, yeah, thanks. I now just see that try to share my screen, I have to allow something in the system. Would you mind to swap over to the next one first? Because I have to do something in my settings on the laptop, which is pretty stupid.
Yeah, see if Scott, are you queued up? You're gonna have to unmute yourself.
There we go.
Okay.
Yeah, hold on. Let me bring my screen up just a second.
So
We'll buy Hans some time.
Let me know when you can see my my screen.
Sometimes it's an adventure getting your screen to share.
There we go. Can we see the screen right now or no?
Not yet.
How about?
There you go, Scott.
There we go. Okay,
Fine.
cool. Well, this will kind of dovetail right into what Emmanuel was talking about. Taking it a little different approach on there. We've, as Paul's going to mention here in a little while, we're talking about the select shift motor, and this particular power section is 7 1/4. It's a 7.872, and right now it's only being offered on select shift. And so wanted to go ahead and let you guys take a look at this one. We're seeing some really good results from it so far. Looking at some of the power of this thing, it is capable of 1,000 horsepower when you combine surface rotation with that at 70 RPM. As we're seeing more and more, people pushing the limits on where you're trying to get to as far as performance output, flow rates, torque requirements. The name of the game is deeper, faster, cheaper. I can help you with 2 of those, but not the cheaper part. So this new motor, it's rated up to 800 GPM. We've got a torque output of just under 21,000 foot-pounds of torque, and you're looking at about 2,000 PSI on the max recommended differential pressure there. And as Emmanuel was saying, also you can see this one is the ERT power section with the even rubber. With those motors, you're typically always going to get higher torque output, higher differential capabilities, and better uniform heat distribution. All the benefits of the even rubber motor applications. Some of these motors you'll have a conventional option versus a standard option, and just 9 times out of 10, unless it's a really benign application, I'm going to recommend going with the even rubber technology motor. Looking at the torque curve and the speed outputs of this one, as you can see at the recommended max differential at 2,000 PSI, we're about $1.80 on the RPM there. And the torque slope of this motor is 10.46. When we compare it to a couple of our workhorse stators that most people are aware of, a lot of people run these, they're pretty standard across the industry, the 7857 and the 7850. The 7872 is a 0.26 rev per gallon motor, so it's not a huge difference in speed. But when you compare it to the 57, we have 33% more available horsepower at the bit than the 57 does. About 16% more on the max recommended torque, 27% more differential capabilities there, and then about 20% more available speed at the bit at max flow rate, which, as we said, is 800 GPM. Speeding it up a little bit with the 5.0, as you know, you're gonna with speed you're gonna lose a little torque. So there's 52% more torque available with this 7872 than it would be with the 5.0. So this is really a beast. 60% more available horsepower, 45% more diff, and only about 10% more available speed, because the 5.0 it's inherently a little bit faster stator. But man, you can see the difference in performance output. This thing's a beast, and that's really what we're allowing our customers to do, is to change their standard operating procedures. Looking at field runs so far, like I said a while ago, this is a brand new power section. I think we've got 11 of them in rotation right now. We're bringing more in daily, but they've only been out really starting since December. So as of March 1st, we've had 18 runs. 2 of those were internal field runs at our RDTC rig. which is just west of Huntsville. So far we've used it in 8 3/4 and 9 7/8 hole sizes. 16 of those 18 runs have been customer field trials. So far, we've limited them to Bakken applications and Permian applications. We focused on verticals, tangents, nudges. There's been 15 of those. And then one was just a tangent curve / verticurve in Williston. One of the things that we're seeing also that's interesting is customers are rerunning this motor where they would normally trip for a bit, and it's still got gas in the tank, so they'll take it, send it back in and rerun it. It's extremely common to run the upper vertical and lower vertical section in Williston, and then some people are running as many 3-bit trips in West Texas, just because it's a beast. So we're seeing some extremely good performance out of this motor. We're very excited about it. One other thing that we're seeing here, we've had 0 chunking. Not a single one has chunked yet. 80% of the runs show the clients are, like I said, they're running them for multiple runs. But I have yet to reline one because of chunking. Now, we still reline them whenever, hot temperatures or oil-based mud or any of those. Actually, I think we're relining all of them right now, no matter what, just to guarantee the better performance. But you're seeing significant ROP advantages due to the higher flow rates, better horsepower output, speed range. Offers the ability to drill extremely abrasive or benign systems, or be able to take into consideration those formation changes. And like I said a while ago, we're really allowing our customers to change their standard operating procedures to be able to keep on drilling reliably here and make those transitions. Because for the Bakken, the first 5,000 feet up there is very benign, but then as soon as you start getting into those higher temperature formations like the Kibbe Lime and that stuff, it gets pretty ratty there, and you can tear a motor up. So this one seems to be performing extremely well so far. As I said, Paul's going to talk about the select shift later on, and right now it's only available on select shift. But man, we're extremely excited about this particular power section. It's doing really good. So that's all I have on this one. We can open it up to questions, or if Walter's ready to go, we can kick it back over to him. However you guys want to do.
Thank you, Scott.
Yeah, we can do a Q&A session at the end. So if Hans Hank, if you're ready.
Yes. Thanks, Scott, for filling me in. I owe you one.
Oh, not a problem.
I had to restart. So no, thanks for that. Yeah, so thanks for, oh, this is not the screen. Try to get full screen. Yeah, thanks for having us here. I would like to talk with you about full metal power, the metal-to-metal power sections without an elastomer, which are of interest, of course, for the hot geothermal drilling in energy and oil and gas. Specifically in the geothermal, of course, for the hot temperature and under harsh conditions. And then specifically, you can also think about drilling with nitrogen and oil-based muds, but specifically the high temperatures are of interest. I would like to run you through a few things. So yeah, we know all what is ongoing with the thin-walled or the even-walled series, where you have a thin layer of rubber, which are a large improvement, of course, to the conventional ones. But we're also dealing with the holy grail, which is actually eliminating the rubber and then also eliminating the possible failures. And of course, there's a lot of improvement on the rubbers, but at the end, you still have limitations on the temperature or drilling with nitrogen and the oil-based muds. But yeah, also the holy grail, which is I think there for 20, 30 years, is to make the metal-to-metal happen. Is how do you create a power section metal to metal so accurate that you will be able to maintain a small gap and still maintain a performance. we have been able to create a process like that. We call that electrochemical machining. It's based on electrolysis, and by means of electricity and chemistry, we're able to dissolve this accurate profile inside of the stator. Just some quick company introduction. At the bottom here, you see 3 companies called ECM Technologies, Easy Profile, and Full Metal Power. ECM Technologies is the company that we started back in 2003, and ECM stands for the electrochemical machining technology. Continuing the company and fully focusing on a more dedicated product, we have set up the company Easy Profile as electrochemical profile, where we are building stators with the technology of electrochemical machining. And since the beginning of last year, we have introduced the Full Metal Power, where we are really focusing on metal-to-metal power sections. So like I mentioned, we already have a longer history, specifically based on the electrochemical machining, which all started back when I finished my study in 1969, where we are working on the electrochemical machining for the shaver heads of the Philly shave, which is known in the US as the Norelco shaver. So the slots, the holes, the polishing, the leveling, 100 million components are machined annually by electrochemical machining. And in '99, we developed that technology for the production of the turbine blades for the Joint Strike Fighter. In 2003, I thought, okay, this is a cool technology. So I started the company ECM Technology as a consultancy. Then the first introduction, because within that time period, we worked for a lot of different kind of industries, for the aerospace, automotive, medical industry. But first introduction into oil and gas was back in 2009, where we looked into the possibility of profiling the stator for an even wall application. In 2013, we built the first demonstration machine. 2017, we found the company Easy Profile. Built a larger production machine, so we're now able to handle up to, let's say, 12-inch in diameter, up to 25 feet in length. Build a second line, 2020, the introduction of Full Metal Power, and in 2021 we will continue releasing different more models from 11116 up to 958, hopefully by the end of the year. We have a facility in Leeuwarden. Leeuwarden is a small city in the north of the Netherlands in Europe, the neighbor country of Germany. And in that facility, we're now building up these production lines. These are lines up to 25 meters in length, and each line can handle the machining of those stators. And the idea is to build up something like 8 to 9 lines within the next 3 to 4 years, only profiling stators and rotors for the metal-to-metal power sections and even wall versions. So a small view on what is the technology and where does it come from. These 2 gentlemen, I think the left one you might know because that's René Monod, the inventor of the Monod principle. So the helical structure that we have now with the PCP and the PDMs. He started the company for pumps back in France in 1930, so roughly 100 years ago. Michael Faraday, you might not know, he's the founder of the case of Faraday, but also the father of the modern ECM technology. And he is also responsible for electrolysis, but also our battery systems. So we use his background. Also, everybody uses it. But that's back in 1834 when he published the Faraday law. So that's 200 years ago. And now, let's say 100 and 200 years later, we combine these both technologies of these both gentlemen to the holy grail, what we call the metal-to-metal power section. We have built now several products, but the focus is on motors, power sections for motors and pumps. So these include the metal-to-metal, but also the even wall versions that we are producing. Besides producing motors, we have also the ability to work on pumps. So we have 2 projects where we are working on developing the stator technology for metal-to-metal pumps. And other options are cracking calls for downstream applications, so where you're profiling large tubes, which can be up to 14 meters in length for ethylene cracking furnaces. And then, of course, there are a number of other applications. Just a small insight of how the technology works. Based on electrolysis, we have a pre-drilled tube. We have a front runner that guides through it very accurately. And this is an electrode, and this electrode dissolves all the metal. So it's not a mechanical machining technology, but it's all based on electrolysis. So by means of electricity and chemistry, we have a small gap here in between, and the electrode erodes or electrochemically dissolves all the metal. And this long shaft here behind conducts a few thousand amps, and at a speed of a few millimeters up to 4 millimeters a minute, we're dissolving this profile very accurately over the length of the stator. And the same can be applied for the rotor. So manufacturing the rotor and the stator with the same technology in the same shop makes it feasible to combine that to a very good performing power section. This is an example of a small 278 where you can see a rather thin gap here between the rotor and the stator. So we have the rotor and the stator here combined, and by maintaining this small gap, this rotor just rotates on gravity and stays on the lower end. And by maintaining this small gap over the full length of a couple of meters, makes it feasible to get some very good, decent power out of a metal-to-metal power section. So what we are doing is we're designing the power section here in-house, and by designing it, we need this electrode, like you saw in the animation. This designing process of the tooling takes 2 weeks, and then manufacturing of the tooling is another 6 to 8 weeks. So within roughly 2.5 months, we're able to present a new design to the market. And what we're providing is we're not a motor developer or a motor supplier. We're in the field of providing power sections, and everybody has its own proprietary technology on bearing packs, bottom ends, top ends. So what we have decided is that we provide rotor stator machined according to our electrochemical machining process, just as a blank. So we're providing blanks without threading, and in that way you're able to add your own threading and have your own bearing packs used. So the take-home message is full metal power, easy profile, full focus on ECM, and ECM. That's where our strength is. And that way we're able to manufacture the best possible metal-to-metal power section. Both rotor and stator will be surface treated in-house to guarantee and optimize longevity. And we try to produce those both in the same facility. And that's what we do for now from the Netherlands, and build up and extend the fleet with the different models over the period in this upcoming year. So for now we have the 278 in production. The 218 will be upcoming this month. We're starting this within 1 to 2 weeks. We have a 5-inch model on the market. It's a low speed version. So we're also working on a higher speed, which will be available by the end of the first half year. The 7-inch has been designed, the tooling has been ordered, so we're expecting that one as well by May, June. And then we have an 8-inch and a 958 on the roll for the second half of 2021. And that's in a nutshell the electrochemical machining and profiling technology of full metal power. Thanks.
Thank you, Hans. Very, very informative. I mean, to be honest with you, as a moderator for this section, I mean, I have a lot of questions. I mean, this is definitely I would call it a game changer. Nevertheless, if you don't mind, I will start with the questions.
Yeah, go ahead.
Okay. So I do see that. First question? Do you make complete motor or just the power sections?
From the Netherlands, we make the power section, so that's where our strength is, and that's also where our knowledge is. But we cooperate with partners in the field So some clients require a power section and they can handle it themselves, but we also have several that just want a motor because that's the standard in the industry. And then we have our partners that we cooperate with, and then we run it by them.
Okay. So given the I saw that you guys making the through tubing application, obviously in nitrogen and the temperature and the geothermal wells, and I do see the application with the, when pumping acid for the, cleaning out paraffins and all the, for the clean outs for the through tubing applications. But when it comes to drilling or even milling something out, do you see any well, first of all, if you pump acid through it, is there any kind of chemical reaction with a metal? That's the first question. And number two, do you see any of the vibrations given the metal to metal power section?
No, two good questions. I think that there is a learning curve we have to make with acids and with H2S, of course. We have a good chemical resistance, but the chemistry and the attack from acid and H2S can be very aggressive. The nice thing about ECM is if you take a metal, we now use pretty well the standard materials which are used in the industry. But if we want to move to very chemical resistant metals like the hastelloys, the inconels, which of course have technically other restrictions, but the electrochemical machining process is not limited to the hardness or toughness of the material. So where you would have conventionally limitations because of that hardness, we're depending on the chemical composition and just dissolve the metal. To give you an idea, inconel could be dissolved faster with the same setting than, for instance, aluminum.
Mm-hmm. Right.
So
I mean,
that gives a good option there. And your second question again was
the vibration.
Oh yeah, the vibration.
Yeah.
No, we had yesterday. We had a 5-inch on the dyno in Houston, and the guy that was testing it was saying, yeah, normal with an elastomer, you see really the vibration. But because of this small gap we're looking at, it was running very, very smooth. And yeah, that's a benefit. But of course, that's also a further development we have to look into. But you can compare it like if you have some space within a bearing pack, a normal bearing, it starts shaking, and due to the shaking, it damages the surface. And we're trying to maintain a gap in the other magnitude of 1 to 2 hair thicknesses in that kind of order. So 3, 4, 5 thou, and maintain that over the full length of a couple of meters.
Okay. And as far as the torque output, I mean, do you see, obviously, do you have any specs on a torque output? In fact, the guy that was doing the testing, I was supposed to meet with him. That's a guy in Dallas that represents you. Is that correct?
Yeah, correct. Yeah. Right. So to give you an idea, the a 278 power section of roughly 2 meters in length runs over a 2000 Newton meter, and the 958, for instance, we have designed right now is anticipated to have something like 30,000 feet LPS. Yeah.
Okay. Well, thank you very much for answering my questions. Obviously, we have a few questions from Q&A session. Scott Powell asking is there a repair option to recoat rotor and stator as it wears?
Good question. Yeah, so when you normally have the elastomer, you replace the elastomer. For us, we have of course the stator and the rotor. Business-wise, for us, it makes sense to have the stator wearing. Because if we make the rotor wearing, then all our clients will start producing their own rotors. So business-wise, for our company, it's that we have the rotor or the stator wearing, because in that way we can control. So the hardness of the surface are in the order of magnitude of 1200 HV, and having one sacrifice with respect to the other makes that the repair principle is more or less just replace it, because it's pretty tough to repair it and then maintain that small gap of a few hairs of thickness.
Thank you. And I would like to apologize to Ron French. He had asked the first question. Do you have any information on how solids affect the power sections, or the brine will affect it? So
No, that's a good question. So brine is not an issue. Actually, brine is the basic material how we machine it. So no, salt levels is not a thing. But solids is a question mark that we have to deal with. The forgiveness you have with elastomer is of course a big advantage. We don't have an elastomer. We have a very tight gap, and that tight gap has its restrictions. But we had one power section just running cement through it, so that's very abrasive. And of course, at the end, you can measure somewhere, but it can handle it. But large particles, yeah, that's a small gap. That's a restriction.
All right.
But we will do an extensive
sorry.
research on that in the future. Sorry.
Well, I was just going to tell Farhad, there's a couple of questions in the chat. Do you see the chat?
Oh no, I didn't see the. Let me see here. All right, yeah. So people asking, I think it's Gozi asking, do you have a rough performance specs for the 5-inch power section? And
Yes.
okay, I guess maybe is it published on the websites that they can go and check it out, or you can send it in the chat?
No, not yet, but send me an email and I'll forward it.
Okay, sounds good. And then the next question is from Tim. You mentioned in-house surface treatment to prevent it. It goes very well with the ECM treated surface. I guess is it a question or is it a comment? I guess.
No, I think what Tim mentions, Tim is pretty well familiar with the electrochemical machining process. So combining a surface treatment with an ECM surface. So an ECM surface is rather smooth, as you might be able to see. It's more or less shiny. It runs on a couple of millimeters per minute through the surface, and the adhesion or the treatment of an surface treatment process runs very well with an ECM surface. So Tim, thanks for that.
All right. Well, thank you very much. It was very informative. Obviously,
actually, there's one more, Farhad.
Okay.
I think you passed on this one intentionally because it's Siva Kumar Mathanagopalan asked the question. You just didn't want to take a shot at the name.
No. I'll go short if it's okay. Siv.
Okay.
Siva, extremely interesting metal-to-metal technology. At these speeds, how do you avoid something like friction welding, let alone performance?
Avoid friction welding.
He's essentially saying that the metals don't bind themselves to each other.
Okay. Yeah. No, of course, the surface treatment itself, but the running the metal to metal in, of course, an environment with the drilling liquids in between, of course, prevent friction welding, and it's not rubbing continuously on the same spot. It's scraping all over. And what we have done with our latest design, that it's rolling over instead of scraping over the surface. So the contact mechanism is also different than you would have with friction welding. But I like the way of the question. Yes.
Sounds good. All right. Well, very, very informative. We have come far since Jim was talking about how decade ago or 2 decades ago or 3 decades ago things were different. I mean, we have definitely come far with even wall, even rubber thickness, power sections, and here we are. So thank you very much to all the presenters, and I'll turn over to Jim to highlight anything or move to another section. Thank you, gentlemen. I appreciate it.
All right. Thanks, Farhad. Thanks, Hans.
Thanks. You're welcome.
Yeah, Farhad, actually, Bill and I were talking about 4 decades ago. As much as it pains me to say that, it was 4 decades ago.
Well, that's good.
But you were just a little boy then, right?
Hey, I probably was in kindergarten. Not even, no, if it's 4 decades, then I probably was not in the plan.
Okay. All right. Well, just to keep things in perspective, right, Bill? Yeah. So thanks again.
Yep.
So that's great. Well, we're just a few minutes ahead of schedule, but I don't see any problems with that. Scott, if you want to go ahead and unmute and introduce Mr. Neal.
Well, that would take a long time if I wanted to go through the whole process. But,
He's one of those 4-decade guys too.
Yeah, a little bit.
Now, I have the unique and privileged pleasure of introducing one of the most versed people when it comes to select shift. Someone that's actually helped me out a lot with bringing this tool to market. Mr. Paul Neal is here today to give us another look at how it's doing. So, without further ado, Mr. Neal, would you be so kind as to queue up?
Yes, of course. Thanks, Scott, for the introduction. Thank you, Jim, for giving me the opportunity to present this technology. Can you give me a thumbs up or a note when you guys can see my screen? Yep, okay. So with that, we'll get started. Thanks for everyone that's still on the line to listen to what we have to say. It's a technology we're very interested in, and hopefully you guys see some interest and value in this as well. Today's presentation, basically at the high level, we're going to talk a little bit about what the tool is, some of the applications, some of the features, and then we'll get into a little more granularity on how the tool shifts and a little bit of run info based on what we've seen in the past and a run we've recently done. So what is it? At 30,000 feet, basically, it's a motor that allows you to change the bend while you're downhole, right? So when you're drilling with it, it steers the same as a traditional drilling motor. We wanted to make sure that the design was comfortable and familiar with directional drillers globally. So we wanted to gear something that wasn't too outside the norm for them. We can use a variety of different power sections with the tool. So you're not limited to one. We'll talk a little bit about that later in the presentation. We also have multiple configurations, right? And we'll talk about that as well further down. Essentially, we have options where we can set the tool up to do multiple shifts, toggle it back and forth, single shifts, pin it in different configs. So we'll talk a little bit about that here in a little bit. And then finally, the other thing is that the tool is fully mechanical. So there's no electronics inside the tool. The mechanism that's used to shift the tool back and forth is mechanical. And then the mechanisms that we use to send the signal to surface to basically inform the operator on which setting the tool is in, whether to be the high setting or the low setting, that mechanism is also mechanical. So basically, we didn't want to have to introduce electronics tool, and we were able to do so very successfully. So what are some of the applications? Predominantly and primarily for us, we were targeting, the reduction in trips, or capitalizing on the tool's ability to change the setting to eliminate transitioning from a vertical to a curve or a curve to a lateral, right? But the more and more we've run the tool, the other opportunities and applications became very apparent, right? So another big focus for us is improving bit life or motor life, right? So reducing the stresses on the bit or the motor based on what bend setting you're using. So, if you're having to drill a hard formation that's a couple of 100 feet thick or whatever the case may be, setting the tool in the low setting, getting through that section, and then kicking it back to where you need it to be to continue drilling. Performance drilling, always a focus. So improving ROP, increasing your RPMs while the tool is in a low bend setting or straight setting to get more horsepower to the bit. Optimizing your torque and weight on bit parameters to improve performance. Improve hole cleaning. So, theoretically, setting the tool in a low bend setting or a straight setting, rotating it faster to get cuttings out of the hole, drilling a more engaged hole, reducing tortuosity, and reducing the amount of sliding. So conceptually, if you're drilling with a concentric BHA, the tool tracks better, not having to slide as much. And then the other, application that we look at is reducing the risk of uncertainty with respect to dogleg inconsistencies, right? So if you're drilling in areas where formation can push you around, you know, I guess unknowingly or inconsistently, or you have a motor in the hole and you're not quite sure if the bend is going to get you where you need it to be, you know, you have an opportunity then to kick up the bend on the tool, get through that area where you're having some challenges in getting dog legs needed, and then once you're through that area to kind of kick it back and get you where you need to be back on track. Some of the features of the tool we wanted to highlight was the fact that the tool will shift within a 2 to 4 minute window, right? And we're going to talk a little bit about that here in a minute, but when we're shifting to the low bend position, so if you're going from a high to a low bend, that can be done while you're drilling on bottom. And then when you're shifting from low to high, that's typically done off bottom during connections, right? So the premise on that and the focus behind that is to reduce the amount of NPT associated with shifting the tool back and forth. If you're making connections within an 8 minute window, the tool will stay in your low bend settings. If connections are typically more than 8 minutes, then the tool will default to the high bend. So depending on what you're trying to accomplish, and normally most connections are within that window. So if you're drilling ahead and you make a connection, the tool will stay in that low bend setting as long as it's within an 8 minute window. With regard to signal, one of the primary, I guess, criteria we wanted to establish is to ensure that when you're at surface, we had some sort of mechanism to know what bend setting the tool's in. So basically, there's a mechanism inside the tool that will send a signal to surface that's about 150 to 200 psi difference. So essentially, what will end up happening is when your tool is in the high bend setting, your baseline standpipe pressure will read about 200 psi higher than what it would be in the low bend setting. So when you're drilling and you're making a shift, you're looking for that signature to see where that baseline pressure sits, and that's basically your telltale on what position the tool is in. And from a specification perspective, you know, torque, weight on bit, so on and so forth, it's equivalent to the Series 50 motor, which is the new platform, which was the presentation that Gozi had sent and gave this morning. So that we basically built the tool on that platform. So getting into a little bit on the shifting, I guess, process, right? So if you look at the top third, I guess, it looks, if it's sitting on the rack, you probably wouldn't be able to tell it's a select shift. It looks the same, right? With all the same bits and pieces, with the exception of the lower end below the bend, right? So inside of there, the locking differential and the locking mechanism is where we put those pieces to allow the tool to shift, right? So everything sits below the bend, which extended the bit to bend a little bit. But for those that have had history running to the Series 36, it's the same as the Series 36. So you're really not losing that much based on our legacy product. So shifting the tool, essentially what will end up happening is if you're drilling, let's say, for example, at 650 gallons a minute, right? So to shift the tool, what you would need to do is lower your pumps to, let's say, 300 gallons a minute. And what ends up happening then is if you're looking at the middle row there, you're reducing your flow. The locking mechanism unlocks the tool, and then your locking differential basically engages. So then going from a low bend to a high bend, tool's unlocked, you're at the lower flow rate, and you're pumping on the tool now, right? But your tool is stationary, you're not rotating it. So you're pumping on the tool, and the torque that's generated from the power section will actually pull that lower end from the low position to the high position, right? Then you bring up your pumps to the full drilling rate, your locking mechanism locks into place, and now you will drill ahead and slide ahead as the tool would be in a high position. And then conversely, if you're going from a high to low, process is the same. You reduce your pumps to the lower flow rate, 300 gallons a minute versus 650. The locking mechanism will unlock, and you're flowing on the tube. But instead of just having the pipe stationary and using the torque from the power section to pull it, you're actually going to rotate the string, and then the stab on the tool creates drag, and that's what's going to pull the tool back into the low position setting. So essentially, you're using torque from the power section to pull it one way, and torque created from the stabilizer on the lower end of the tool to pull it the other. And that's basically how you toggle the tool back and forth. From a configuration perspective, we have two sizes. We have a 7 1/8 and a 5 1/4. The 7 1/8, we have bend settings that sit anywhere between, multiple settings that sit between a 0 to a 238. And the power sections that you can run anywhere between a 0.08 to a 0.33 revs per gallon. To Scott's presentation earlier, the 7872 is one of the power sections that's made available on the selection. In the 5 1/4, we have bend settings that sit anywhere between 0 to 2.0, and power section configurations for that are power sections that sit between the 0.6 to 0.8 revs per gallon. Tool configurations, we can set the tool up as a single shift or a multi-shift. So what that means is you can set the tool such that when you make the shift, the tool will only shift once and it will stay in that position. Or we can set the tool up such that you can toggle the low-high settings back and forth as many times as you need, right? So we have both options depending on what your objectives are. We also have an option where you can run the tool slick. So I mentioned in the previous slide where you use drag on the stab to pull it to the low position. If you run the tool as a single shift config, you can actually run it slick. We have a way to set the tool up such that it will pull back into the low position with a slick assembly. But again, that's only for the single shift. We also have options where you can pin the tool in the high and the low setting. So what that means is if you're drilling ahead, we can pin, let's say you're drilling from the curve to the lateral, we can pin the tool in the high position, and whatever you're needing to do with flow rates and so on and so forth, the tool will stay into that high bend setting. And then when you're ready to land or drill your lateral, you basically flow at about 100 gallons a minute above your normal drilling flow rate. The pin shears, and then the tool will either do the single shift or you can continue to do a multi-shift. So there's a lot of variety on how we can configure the tool. It really depends on what the application is and what your needs are. With respect to runs, basically as of the end of Feb, we were touching on almost 100 runs. We'll hit that this month. Total footage, we're creeping up on about 350,000 feet and about 3,300 circulating hours. Breakdown of runs, 25 of those runs have been NOV tests. So 18 of them have been at RDTC, which is, Scott mentioned, the test facility in Navasota, the NOV test facility in Navasota, and then the remaining 7 have been at Catoosa. The remaining 72 runs have been client-facing, right? Predominantly vertical tangent, but we're starting to creep more and more into the tangent curve. We've got some runs curve laterals and laterals. The majority of our runs have been in the Bakken, but we're consistently getting some more and more opportunities in the Permian. But we've also done some stuff in the Eagle Ford and the Marcellus. So from a run breakdown perspective, that's basically where we're at. And to close out the presentation, just a run we just recently had done. The objective of the client was to drill the vertical and the curve section, maintaining performance KPIs, right? So we set the tool up with a 1.5 to a 2.25 degree send. We ran the 7850 power section. We drilled the vertical section with a 1.5 degree setting. We got to the kickoff point. We shifted the tool from the 1.5 to the 2.25, and then we continued, then drilled the curve, landed it, and pulled out of the hole. Run was about 3,500 feet. And the max dog leg on it was about 15 degrees. So with that being said, I'm looking forward to answering any questions that you might have. Scott? Hey, Scott, are you there?
He's got a, Scott,
He's
you got
gone.
on mute.
Okay.
For some reason, my mouse quit working, and there we go. Now it's back.
Yep.
Thank God for Surface. I was actually able to use the touch screen and bring this thing back to life. Okay. Well, thank you, Paul. That was extremely informative, and I still think you did a better job than I did before. So. No, that was really good. Thank you so much for that. Let's see here. I don't see any questions on the chat there. Jim, do you see anything coming in on?
No, I think we're clean.
Okay.
I think we explained it so well that nobody had any questions.
Or put everyone to sleep.
It's
Yeah.
either one, so.
Well, it's always tough being the last one before lunch. Actually, there's one popped up in the chat there, Scott. You see it?
Yep. So Paul, Yulin Shin asked if how do you determine if the shift is successful?
Yeah. So I guess the mechanism that we use, there's a mechanism inside the tool that creates a pressure drop depending on what that position the tool is in. So what ends up happening is when the tool, if let's say we're running in the example that we just had with the 1.5 to 2.5. So when the tool is in the 1.5 position, you're going to take a baseline, and let's say your baseline is reading 3,300 psi, right, on your standpipe pressure. When the tool, you downlink to the tool shifts, and now the tool is now in the 2.25 position. So instead of reading 3,300 psi on your standpipe, you're going to see about 3,500 psi on the standpipe. So basically, as you toggle back and forth, you're going to see a slight difference in your standpipe pressure depending on which position the tool is in, and the tool will actually give you a higher pressure reading than what it would be if you were in a low position. And basically that baseline will stay consistent until you shift it back. So that baseline will hold that 200 psi higher until you want to shift back to normal. Then when you shift that back to normal, the baseline will shift back to 200 psi, so that you're using pressure to indicate what your position's in. Yeah, but that's how we do it.
And I can vouch for that. I remember the first time I ever saw that up at Catoosa. It was extremely interesting and evident when you can actually sit and you sit there and watch it on the screen as it, it's like we're in high bend, we're in low bend. So thank you for that, Paul.
Plain as day. Yep.
We have another one from JJ Herman. Says, would there be an AI software which could handle the readings to actually provide the driller with a shift indicator for user friendliness?
Yeah, so AI, I'm not sure if you're alluding to, what tool we should, or what position the tool should be in to get to that objective. But I think what we do have is a set of tablets that the operator will use, right? So what essentially ends up happening is you preload the tablet with the drilling parameters that you're going to run on the tool. And then when you're ready to make the shift, whether it be the high or the low, the sequence at which you would need to do to run it, the tablet basically will run the sequence for you. So you're looking at the tablet and you're monitoring what you need to do in order to shift. So it basically just walks you through that whole process. But as far as AI integrated to say, now you should be in high or you should be in low, and we're not quite there yet. That's basically how we run it. Yeah.
Fair enough. I was hoping you're about to impart some brand new secret squirrel technology that I hadn't heard about yet.
Not today. Not today. I guess the other thing to mention as well is with regard to support. It's not your standard motor, right? And we do actually send people to location. to support the technology. So what ends up happening is we will have guys that will go to the rig that are there to work with your directional drillers, that are there to work with your drillers, on the break, and it's to show them how to shift the tool, to give them some visibility on where the baselines are sitting and how to tell between the two. There's other indicators that we use when we shift to see when it breaks over and things like that on the EDR system. But we also look at and ask for real-time data stream, right? So when there's jobs running, we have people Houston-based that are watching the jobs in real time, so that if there's any questions or concerns, those guys are seeing that data as the driller is seeing it to provide support. So we do have different ways to ensure that when we're shifting the tool, we've got multiple sets of eyes and some technology in place to support it.
It's probably also worth noting that, if there's a client that has a long-term relationship with a directional company or something, we have had people come out to our RDTC test rig and go through training to understand the process a little bit better, because like Paul said, it drills like a regular motor once it's in the hole, but it does require a little bit of understanding on how to make it shift, and the parameters to be within. And so, we do have that availability as well if people are interested in, sending some people out to learn on this a little bit more. So
yeah, we have. So that's a great point. We have classroom training that we give and that we have given to directional drilling companies, and we also have a practical side of it, on the job side that you go to our TCC or we go to one of the wells that we're drilling to show them how things are run. So we do have things in place to support the directional drilling companies on how the tool shifts and to recognize those signatures.
Well, hey, Paul, where has most of the interest come from this? Is this coming from the operators themselves, or is it coming from the directional companies?
Yeah, a lot of the interest is more operator side, right? So
Okay.
we've talked to a lot of operators, and they see a benefit. There's definitely interest on the directional driller side as well. They see a benefit as well, to help them to compete against other technologies. So yeah, it's from both sides, Jim, but predominantly from the operator side.
Go ahead, Paul. You can say it. It competes against a rotary steerable.
Yeah, not today. Yeah, no, and to that point, Jim, I think it's interesting, right? So you look at the landscape on the directional drilling side, and there's a segment that's I guess very motor driven, right? Economically, performance wise, it makes a lot of sense. And then there's a segment that sits on the rotary steerable side. That from an economic standpoint, it makes a lot of sense. From a performance standpoint, it makes a lot of sense. And then there's a gap in between. And I think with the select shift, there's an opportunity there to help bridge that gap somewhat. Right. So there's a little bit of area there for us to play in.
Yeah, I was texting Scott while you were doing your presentation, so I'm already keyed up for the next one.
Sure.
So, Scott, there's a question in the Q&A if you can see it.
I was looking at the chat. Sorry.
Yep.
This is from Oscar Sanchez. It says, from the presentation, it's understood that shifting to low is done while on bottom. Would it be required to pick up off bottom to ensure the pressure drop confirms the successful shift? It would not be clear 100% of the time to do it while on bottom, as pressure differential would fluctuate as the bit changes.
So that's very observant, right? And you're right? So essentially, to a certain point. So what ends up happening is what we see when there's a customer who is running the tool for the first time, first run or so, they will consistently pick up off bottom after a shift is made to confirm baseline pressure, right? So now, said that, if you're drilling a low tangent or a vertical section, for example, and you're running the tool in the 1.5 degree setting, they're not picking up after every connection to confirm, right? So they make the connection, the tool stays in the low bend setting, and it will stay in the low bend setting, right? And they're not confirming that. They will confirm sometimes after a shift is made, right? But what typically we're seeing is when the customer gets more familiar with the technology, they're not relying solely on baseline pressures, right? So what they're seeing now, let's say, for example, if they're going from a high to a low, they make the shift. Instead of picking up off bottom, they're comfortable with using things like torque, torsional vibration or vibrations in itself, and they use that as the cue to determine if the tool had shifted or not, especially when shifting the tool is not been a major issue, right? So they're just using other parameters other than the baseline pressure to do it. Said that, the baseline pressure is the surefire way to tell if the tool is shifted or not, right? So I guess to answer Oscar's question, yes, but it really depends on how comfortable the customer is with shifting the tool and the data that they've used and seen prior to running the tool to know where the tool is sitting, whether it's be at the high or the low bend position.
So basically what you're getting at then is once they're more comfortable with it, there's other characteristics that they're noticing. They see the torque fall off, they see the vibrations fall off. They understand the environment that it's creating.
Yep.
And they're able to verify, okay, I shifted back to this now. And like you said, it stays in the low bend setting, which that's a relatively new development compared to the first iteration of the tool, right? I mean, that's within the last year, right?
Yeah, so that's been about a year. You're right. So it hasn't been around that long. When it comes to the evolution of the technology, we weren't able to shift on bottom, right? So all the shifting happened off bottom. We would have to make shifts after every connection, depending on what configuration we're in. I think our initial shifts times would take 8 minutes plus, and now we're down between 2 and 4. So since we started the project, the tool has evolved quite a bit. We're at a stage now where the shifting mechanism is extremely reliable. We're not worried about how the tool shifts. The signal recognition is very reliable. It's just more focusing now on getting performance and running the tool as needed for it to perform. Yeah.
Paul, can you comment at all or maybe expand a little more on some of the performance enhancements you've seen?
Yeah.
I mean, Scott was talking about, running the 7.2 with select shift only. It's only available there, but can you comment a little bit on what kind of performance improvement you've seen?
Yeah. So, I mean, it's some of the case studies and the investigations we've done, the glaringly obvious things that really pop out is shock and vibration, actually. So when we're comparing, a tool that was set up as a 0 to 2.0, let's say, right? So it's a straight to bend setting. When we're drilling with the tool in the 2.0, you can see on the data, the surface torque fluctuation. You get the downhole data and you see stick slips, the fluctuations in stick slip. And then you see the shift, and then the torque flattens right out, stick slip flattens right out. So, from a shock and vibration standpoint, depending on what your configs are, we see a significance in shock and vibration reduction when running the tool. The other side of it is pushing your drilling parameters on the lower bend settings, right? So if you're accustomed to running a 183 or 1.5 in your, let's say, your tangent section, and you set the tool up as a 0 to 1.5 or 1.5 to 2 or whatever the case is, just pushing a little bit on your RPMs, pushing a little bit more on your weight when you're in that lower bend setting really helps improve your ROP. And I think the other one is bit life, right? So areas where you're drilling through formation and then you hit the 2 to 3 to 400, 500, 600 foot sections or whatever it is, that's a really hard rock drilling, right? Shifting the tool into the low bend setting and then just going through that section, repeatedly we've been able to save and reduce the bit or improve the bit dull through these harder formations coming out the backside then to get to kickoff point or whatever the objective is, right? And I guess, you know, from a hole cleaning perspective, we've seen opportunities where, or we've had opportunities where just rotating the bit a little faster to get cuttings out of the hole to help with ROP, that's helped as well. So yeah, Jim, to your point, there's been numerous occasions where we've been able to improve drilling performance, improve bit life, just by shifting the tool back and forth as needed.
Okay, good. I think we've answered all the questions. We've ended up here pretty quickly on time. So,
Paul, if you don't mind, also Oscar Sanchez asked if you could post your contact information over there on the chat. And so
yeah, I'll do that.
Wants to reach out to you separately.
Yeah, it's not a problem.
all right, thanks a lot, Paul. Thanks, Scott, as well.
Thank you, guys.
Just a quick, coming attractions. Next week's going to be a reasonably busy week. We've started, or this will be actually an organizing committee on the Drill Bit Industry Technical Steering Committee, DBITS. That will take place next Tuesday, and we've got a panel set up to address that. And then Dr. Rebella Samuel has basic torque and drag training course next Wednesday. And then Friday, I know Scott's been looking forward to this, the Sweetheart Shoot Sporting Clays tournament. It will be up at Blackwood Gun Club. That'll kick off around noon. And looks like it should be a good day for the shoot. This was actually scheduled a couple of weeks ago, but since Scott couldn't make it, we went ahead and rescheduled. Because these shoots are never the same if Scott's not there. So I want to thank everybody again. This has been a great discussion. We've covered a lot of good ground, a lot of good questions. And so keep a good eye on the events coming up, and everybody have a safe and productive afternoon. Talk to you soon.
Thanks, Jim.
Thank you, Jim. We appreciate your time today.
Thanks a
Thank you.
lot. Appreciate it. Have a great
Thank
day.
you, Jim. Bye-bye.